Hello, this is Tisha Nichols, and this is the first video in AP2 Thermodynamics unit on kinetic theory. The essential question is, how can kinetic theory be used to explain and predict the behavior of thermodynamic systems? Kinetic theory is really just the idea that if you zoomed in on literally anything, you would see that all objects, liquids, solid gases, plasmas, are actually made up of particles that are moving. Now, in a solid and a liquid, those movements are kind of bound by the molecular forces holding them together. But in gas, because the particles aren't stuck together, these particles are constantly like running around and colliding with each other and colliding with the container walls. You can see in this diagram, this is known as Brownian motion, and it's statistically sort of random. The paths of those particles are kind of tracked, and you can see that those particles change direction all the time when they collide with each other and with the container walls. You'll notice I highlighted the word colliding. It's a really critical word in this unit, and you're going to explain a lot of things in thermodynamics by using the words collisions. All right, let's blast through the variables we're going to be using in this unit. Some of these will be a repeat, some of them might be new, so pause on the ones that you need. So we're going to be concerned about the mass of atoms or molecules. If you've looked at a periodic table in depth, hopefully you'll know that there is a spot on the bottom of each periodic table element known as the atomic weight. Really, that should be atomic mass, but in any case, the atomic weight tells you how big what the mass of that element is measured in atomic mass units. This may be a little different than what you heard in chemistry, but this is the physicist's perspective on a periodic table. So for hydrogen, where it says 1.008, that's 1.008 atomic mass units. And on your equation sheet, you will see that one atomic mass unit is equal to 1.66 times 10 to the negative 27th kilograms. So if you wanted to know how big a single hydrogen was, it's 1.008 times 1.66 times 10 to the negative 27th kilograms. You don't usually have to do calculations with this necessarily, but you should be aware that it's a very small number, right? On the order of 27 zeros before we actually start getting to significant digits. Oxygen, of course, is 16 times heavier. It's got atomic weight of 15.99. Sometimes we're interested in the number of molecules, which is big N, or the moles of a molecule, which is little n. Number of molecules is if you could actually count up all the gas molecules. Usually you can't, so we usually measure gas in moles, which is kind of like a molecular dozen, except it's a whole lot more than a dozen, right? So a mole of anything is 6.02 times 10 to the 23rd of that thing, and that's known as Avogadro's number, also on your equation sheet. Incidentally, that Avogadro's number was chosen so that that many molecules would have a overall mass of the atomic weight in grams. So 6.02 times 10 to the 23rd molecules will also weigh 1.008 grams if you're talking about hydrogen. And perhaps you learned that in chemistry. Of course, we might be measuring the volume. We will be using meters cubed primarily, depending on the shape of the container. Gas molecules fill the container completely. Two new ones, perhaps, are thermal energy, which we will measure in joules, like all energies, and temperature, which is in physics measured in Kelvin. Both of those two variables are related to the kinetic motion energy of the moving particles. So since the particles are moving, they have kinetic motion energy, and we can use that to calculate those two variables. We will also be talking quite a bit more about pressure, which is measured in pascals. And from a kinetic molecular theory perspective, we're going to be thinking about pressure as caused by the force of the molecules that are colliding with all of the walls of the container. So since all molecules have mass and velocity, all molecules are going to have kinetic motion energy. You may have learned about kinetic motion energy or just kinetic energy in a prior physics class. The idea is that any object that has mass and velocity carries with it this kind of energy. And you probably learned about that about macro objects, big things like balls and rocks and things that were falling. But it's also true for tiny microscopic atomic level things and molecular level things. And actually the same equation holds true. So K, which is the kinetic motion energy of anything, is equal to 1/2 times its mass times its velocity squared. You'll notice that in this equation, there's a linear relationship with mass. So bigger objects have more kinetic motion energy, and that's true for gases too. Bigger gases will. And faster objects also have more kinetic motion energy. But because that V term is squared, the velocity actually matters more than the mass. Doubling the gases or whatever object it is velocity actually quadruples the kinetic motion energy of that object. So that relationship is worth knowing. You can see perhaps the reason for this. When you have cool gases, we have these particles moving around very sort of sluggishly, and they don't run into each other. There's not as much energy in the collisions. And the hotter the gases get, the more and more the energetic collisions become. And also the heavier the objects get, the more kind of energy they carry in those collisions. These vigorous movements and jiggling of all of the atoms actually cause the entire object to expand against its surface tension or whatever's kind of holding it together, whether that is a gas or a liquid or a solid. And this is actually the basis for how thermometers work. If you've heard of thermal expansion, or when you heat things up, they get bigger, right? This is the reason why that works, because those atoms sort of force their container to get bigger as they get more energetic. So this kinetic motion energy is used in finding two very important variables, the internal energy and the temperature. The average kinetic motion energy of the molecules in a gas system can be converted to the temperature, measured in degree Kelvin with the following conversion. So in this equation, K represents the average kinetic energy of one of the particles in any kind of gas system. And if you want to convert that to the temperature of the whole system, you take 3/2 times this Boltzmann's constant, 1.38 times 10 to the negative 23rd joule per Kelvin, times the temperature. So this equation can be used either direction, right? If you happen to know, for example, the mass and the average velocity of a gas molecule, you could use that to find the kinetic energy of an average gas molecule in a system, and then you could use that to find temperature. Or you can go the other way. If you know the temperature of a system of particles, you can actually reverse this conversion to calculate what the average kinetic energy of a single gas molecule is. You'll know that conversion factor is like a really, really tiny amount of joules per Kelvin. That tells you that, you know, even hot temperature gases, an individual particle has a very small amount of energy. It's because they're so small. Even though they're moving relatively fast, they're still really tiny. Using this conversion, you'll discover that there's a few key temperatures you should know. 273 Kelvin is the temperature at which water freezes. If you have taken chemistry, you know that that is known as 0 Celsius, but we're going to convert it into Kelvin. So Celsius plus 273 gives you Kelvin. And that you could have a temperature of 0 K. That is known as absolute zero, and that is theoretically the temperature at which the particle has no kinetic energy. If you plug a 0 in for temperature there, you get a K of 0 as well. So absolute zero is not attainable anywhere in the universe, but we're very close to it in a couple places, laboratories and deep space and that kind of thing. So the slower the particles are, if you could almost slow those gas molecules down, you would be close to reaching absolute zero. The other variable, instead of dealing with the average kinetic energy of the particles, actually is the total kinetic energy of all of the molecules. This is known as the internal energy. So internal energy is a function of both kinetic energy, how fast the individuals are moving, and how many of those individuals there are. The greater the number of individuals, the greater the amount of internal energy an object or a system of objects will have. So I just wanted to make sure you guys saw both of those early. We're going to spend a lot more time on this variable, U, which is super important later on in this unit, but I wanted to introduce it now here with temperature because they share some commonalities. So a thermodynamic system contains a large number of gas particles at what's known as equilibrium. This means that everything is sort of evenly distributed through the system, but it doesn't mean that all the particles have the same velocity. Equilibrium, you will, if looking at a sample of gases at equilibrium, you would notice some particles moving very fast and some particles moving very slow. The particle velocities at equilibrium are distributed along a bell curve of probability, where the center of the curve sort of tells you what is the average velocity. If you were looking to figure out the temperature of that system of gases, you would just use that center value or the average velocity because that's what you use in that Boltzmann's conversion. But you should know that it doesn't mean that every single gas particle in that system is really considered at the same temperature. I mean, they're centered around this center of temperature, but some of them are moving faster and are hotter, and some of them are moving slower and are cooler. When those molecules collide with each other in those collisions, they're going to transfer energy from one to the other. So a single molecule won't always keep the same velocity through time. But an interesting thing about that transfer is that there is no waste of energy during the transfer. This is known as an elastic collision. It's like a perfectly bouncy collision where the particles don't squish, they don't rub, there's no friction. So that means that energy moves around in the system through these collisions, but we don't lose any if we're considering this to be a closed thermodynamic system. This also means that the overall internal energy of the closed system is conserved, right? We're moving it from particle to particle, but keeping it all. And that the temperature must be constant as well, because if we keep the same number of particles in the system and we keep the same total energy, that means the average energy of the particles will be constant as well, and that can translate into temperature. So from our last unit, we know that pressure is defined as force over area. And in the context of thermodynamics, gas particles are going to be colliding with their container walls. And that's where the forces come into play, because each time a collision happens, there is an equal and opposite force, one force that is hitting the molecule and bouncing it around on the molecule, and then an equal and opposite force on the container wall from the molecule. So when we're talking about pressure, you're looking at what is the total force from all the collisions that are happening with a container wall. And that total force is going to have a relationships with a bunch of the properties of the gas. So for example, there will be more force involved in the collisions if the masses of each particle are higher, right? The heavier the particle, the more force it exerts when it collides. The more particles are in the system, the more collisions are going to happen. That means there's going to be more total force. And then the bigger the change in velocity of a particle during a collision, the more force it's going to exert. I highlighted that little delta. This is a little thing, but it seems to get tested disproportionately a lot, in my opinion. Delta V is actually equal to 2V, right? Because an object coming in at V that bounces out at negative V perfectly elastically ends up changing velocity by 2 times the velocity it came in at. So just note that there is a relationship there that is double the incoming velocity, affecting the amount of pressure and force. Okay, we've reached the end of the video. If you wish, take a few minutes to examine your essential question and revisit how kinetic energy can help us explain and predict the behavior of thermodynamic systems. Thanks for watching.